Testing 1, 2, 3. Here I go. Give me that microphone. Give me that microphone.
All right, today we're going to talk about circuit simplification. Circuit simplification consists of a whole bunch of different techniques that allow you to solve circuits more simply. Turns out that KVL and KCL is probably the most difficult method to solve a circuit. However, there are other things, we can call these tricks, to help simplify circuits and make them easier to solve. The first one we're going to talk about is series parallel reduction. And in series parallel reduction, we rely upon what we know about how series resistors and parallel resistors combine together. Now, just as way of a reminder, let me remind you that series resistors are resistors that are connected end to end like this. So if that's resistor 1, there's resistor 2, there's resistor 3. They would have the same current passing through them. So resistors in series have the same current. The voltages across each of these would then add together. And something else about these, if you want to combine these into one equivalent resistance, let's call that an equivalent REQ resistance, I can combine all of those together just by summing up the individual resistances. Over ever how many there are 3 in our example here, so this would be R1 plus R2 plus R3. Now the thing about combining resistors this way is that REQ is always going to be greater than the largest individual resistance. This is for series resistors. Now, if we have resistors in parallel that maybe look like this, here would be the terminals, there's resistor 1, resistor 2, and resistor 3 in parallel, these resistors would have different currents. The current going through each one of these is not necessarily the same. It would only be the same if all 3 of those resistance values were exactly the same. So the current that may be coming in here is divided down each of those 3 paths there. However, it does have something that is the same, and it is the same voltage. So resistors in parallel have the same voltage, resistors in series have the same currents. But the currents that go through these parallel resistors all add together. And what I mean by that is that each of those currents there would add together to be whatever this first current is coming in. That's nothing but KCL applied here. Just like this is nothing but KVL applied, the voltages will add up around a loop. Well, here the currents will add up at the nodes. Okay, if I want to combine all 3 of these resistors together and make one equivalent resistance, then I combine them this way. 1 over each of the individual resistances is equal to 1 over the equivalent resistance that way. Now if you do that, then the equivalent resistance is always going to be smaller than the smallest individual resistance. Something else regarding these parallel resistors is if I only want to combine 2 resistors, and usually when you're combining 3, you might combine 2 at a time and then take that combination and combine it with the third one. So combining 2 resistors at a time is a very common thing to do. Then if I'm just combining 2 resistors, then the equivalent resistance can be written as product over sum. So if I'm just combining R1 and R2 here, it would be R1 times R2 divided by R1 plus R2. And if you solve this equation here for just 2 resistors, you'll see that the equivalent resistance turns out to be that. So sometimes that's handy for people when you just need to combine 2 parallel resistors. This is for parallel resistances here. I say all of this right here as review because we've talked about this before. Nevertheless, now we're going to use series and parallel reduction methods to solve a circuit. Let's start with an example that's in a textbook. All right, this is our circuit here. And what we want to do is we want to find some things. And let's see, what do we want to find? Let's find this voltage. That's the voltage across the current source here. That would also be the voltage across the 30 ohm. So if we could reduce this down to just one resistor and one source, we could easily find that right there. So we want to find that, but we also want to find a couple of other things. So let's find V. Let's also find the power for this 5 amp source. That's the only active element in this whole circuit. So how much energy is this 5 amp source supplying the rest of the circuit in units of joules per second? So what's the power? So power for the 5 amp source. And while we're here, let's also find the power of this thing that's down here on the end. So the power for the 10 ohm resistor. Those are the things that we want to find right there. All right, we're going to use series parallel reduction methods in order to figure this out. And one of the first things we're going to do is reduce this down using series and parallel combining to find an equivalent resistance for this. Now you look at this and you need to be able to quickly and easily determine which of these resistors are in series and which are in parallel. If you look here at the 6 and the 10, those have the same current there, so those two are in parallel right there. So if I redraw the circuit, where now I combine the 10 and the 6 together to make a 16 ohm resistor. This is still the 64, still the 7.2, still the 30, this is still V, and this is still the 5 amp source. Okay, well that reduced down one resistor. We got rid of one out of that. And now by doing that you can see that the 64 and the 16 are now in parallel. So we should be able to combine these two together using our parallel combination method. So let's do that and I'll redraw the circuit again. And now this one is the combination of these two right here. So this one is going to be 64 times 16 divided by 64 plus 16. Now, what does that turn out to be? It turns out to be 12.8 ohms. That's what that is. Okay, we're getting close. We can now combine the 12.8 and the 7.2. So let me put that down here. I'll redraw that. And now the 12.8 and the 7.2, let's see, that's 12, 9, 20 ohms. Okay, now we have kind of reduced this down. Everything at this point has the same voltage across it. But I can also combine at this stage the 30 and the 20 together here. So I'm going to scoot over here and redraw the circuit one more time with those two combined. And this is now 30 times 20 over 30 plus 20. So 660 divided by 5 is 12. So I've got a 12 ohm equivalent resistance is what all of this up here equates to. Okay, now that I'm at this stage, I can figure out what my voltage V is right here. Let's write that right here in this area. Voltage V is just going to be I times R. So that's what we've called Ohm's law. Now, since we're talking about a resistance here, that means that we're dealing with this element here. The current, you can see, has a direction associated with it, and the current is coming into the top of this 12 ohm resistor, so that means it's going into the positive terminal. So do I write V equals IR or V equals minus IR? And I write V equals plus IR. So this right here is the equation we need to figure out what that voltage is. The current is 5 amps, and R is 12 ohms. So that's going to be 60 volts. There. We've just figured out what the voltage is. We've got that one now. Okay, so we got V equals 60 volts. Now that I know that, I can figure out what the power that's being supplied by the 5 amp source is. Now look at that, and I need to figure out the power for that. I need to use P equals IV, or do I need to use P equals minus IV? Look at the direction of the current. You can see the polarity of the voltage here is the same across both of these. So this is the high potential side up here. This is the low potential side down here. The current is coming into the negative side of this source. So if I want to figure out what the power is for the 5 amp source, I need to write P equals minus IV. All right, plugging in the numbers, that's going to be minus I. I is 5 amps times V, 60 volts. And that turns out to be 300 watts. And I know it's kind of hard to see there on the edge of the paper, but that says negative 300 watts. The negative sign here indicates that it is supplying energy. All right, so we've got that one now. Okay, next step, we need to figure out what the power that's being absorbed by this 10 ohm resistor. Now the power being absorbed by the 10 ohm resistor is going to be dissipated as heat. So another way to say that is the power dissipated by the 10 ohm. Power absorbed or power dissipated means the same sort of thing. Okay, now in order to do this, we've got to work our way back up here. And to figure out the power through this, we either need the voltage or the current through this 10 ohm in order to accomplish this. So what does that mean? We're going to be working our way back here. So let's go up here and define some currents. Defining these currents will really help us. Let's say we call the current through the 30 here, let's call that I sub A. And then the current that's going here is I sub B. Now think about that. This 5 amp current is coming, and when it gets to this node, it's splitting. Some of it's going down I sub A, some of it's going down I sub B. Then when I sub B gets to this point right here, some of it is splitting this way. Let's call that I sub C. And then some more of it is going down this direction. That's I sub D. So it's really I sub C I'm interested in here, because finding I sub C is going to allow me to figure out what the power dissipated by the 10 ohm is, because then I can just use I sub C squared times 10. And that'll tell me the power of the 10. Okay, well, let's work our way down here then. If this is I sub A, this is still I sub A in this drawing. And this is still I sub B. This is still I sub D, and this current here is still I sub C. So even though we've combined the 10 and the 6 together to make the 16, it's still the same current going through both of those. You can see that here. All right, let's take this another stage down. This is still our current I sub A. The current here is still I sub B. However, notice that I sub B is this current going also through the 12.8. So these two currents right here combined make I sub B. In other words, if you were going to write a KCL equation for that node right there, it would look like I sub B is equal to I sub C plus I sub D. Okay, so once we've got I sub B, we can figure out maybe what I sub C and I sub D are, perhaps. All right, so we've got I sub A and I sub B here. Then down here we also have I sub A, and this is still I sub B. So all we did is combine the 7.2 and the 12.8 to make the 20. The current is still I sub B. And now you can see the 5 amp here is really the combination of I sub A and I sub B. So the 5 amp current that's going into that node right there, 5 amps is equal to I sub A plus I sub B. So we can't really draw our current here because we already know it, it's 5 amps. All right, well at this stage then, we should be able to go along and see if we can figure out what all of these currents are. We'll go back here, and we know that there's a 5 amp current going through here. We know that the V is 60 volts. Since V is going to be 60 volts here, it's also 60 volts here. So the voltage across each of these is 60 volts. Everything here is in parallel, so everything has the same voltage, so everything is going to have 60 volts across it. Now, with that information then, I can figure out what I sub A and I sub B are. Let's pull this up a little bit, and we can write an equation for I sub A and I sub B. I sub A is going to be the voltage V over 30 ohms. Okay, well that voltage is 60 volts divided by 30 ohms, so that's 2 amps. So we've got 2 amps for I sub A here. Now, from that you can probably see that I sub B is going to be 5 minus 2. It's going to be 3 amps. However, you could have also computed it as well the same way, because it's going to be V over 20 ohms. So that's 60 volts over 20 ohms, and look, that is 3 amps. Okay, so here we have I sub A and I sub B computed. That's the same up here. And if I know what I sub B is, I can now figure out the voltages across all of these elements. I know the voltage across the 30 is going to be V, 60 volts. The voltage across both of these combined here must also be 60 volts. But how does the voltage divide? I'm going to have some voltage across the 7.2, some voltage across the 12.8, and those two voltages must add together to be 60 volts. So I should be able to figure those out at this stage. Let's do that right here. The voltage across the 7.2 is going to be I sub B times 7.2 ohms. Well, I sub B is 3 amps times 7.2 ohms, and that turns out to be 21.6 volts. So there's the voltage across the 7.2 right there. Now let's do the same thing for the 12.8. There's a couple of ways we can do this. You recognize that the voltage across the 12.8 must equal 60 volts minus 21.6 volts. Okay, that's one way to get to the answer. The other way to get to the answer is to recognize that it's going to be I sub B times 12.8 ohms. I sub B is 3 amps times 12.8 ohms, and that turns out to be 38.4 volts. That's the voltage across the 12.8. Now let me confirm that 60 minus 21.6 is also 38.4. And indeed it is. So it checks out. Okay, now that I know the voltage across the 12.8 is going to be 38.4, then that voltage of 38.4 is also the voltage across this combination up here. So the voltage here is the same as the voltage across these two elements here. Both of those are in parallel, so they're going to have the same voltage, and that voltage is going to be whatever it was here, the 38.4. All right, so that will allow us then to figure out what I sub C is. Let's do that at this point right here, down here. I sub C is going to be V over its R. The V is 38.4 volts divided by the resistance here, and the resistance is going to be 16 ohms. So 16 ohms, that turns out to be 2.4 amps. So we have 2.4 amps for I sub C here. Okay, at this stage we can figure out the power. But while we're here, let's figure out what I sub D is. I sub D should be I sub B minus I sub C. So I sub B minus I sub C. I sub B was 3 amps minus I sub C, 2.4 amps. That turns out to be 0.6 amps. Okay, that's one way to get it. The other way to get it is to recognize that it's going to be V over R. The voltage in this case is 38.4 volts divided by its resistance, and its resistance is 64 ohms. Remember, these two have the same voltage, so that's where the 38.4 comes from, divided by 64 ohms, and that turns out to be 0.6 amps. Okay, it's nice when it works, but we were just double checking anyway. Okay, now we know what I sub C is. I sub C was that 2.4 amps, so we can figure out the power for the 10 ohm. And the power for the 10 ohm is going to be its current squared times its resistance, which is 10 ohms. The current is 2.4, so 2.4 amps squared times 10 ohms. That turns out to be 57.6 watts. So there is our answer for the power for the 10 ohm. So we've got now that. Once again, voltage that we were after is 60 volts. The power supplied by the 5 amp is negative 300 watts. And the power that's being dissipated by the 10 ohm is 57.6 watts. You may wonder, well, we didn't ask the question, do we need to write P equals minus IV or P equals plus IV? There's no concern here for that because the current is going to be squared. And when we write this down, we know that this is a passive element. It is always going to have a positive power because it is absorbing the energy and dissipating it away as heat at a rate of 57.6 joules per second. A joule per second is a watt. Okay, so we've just solved this circuit using our series parallel method of reduction. And you may say to yourself, that didn't seem that simple. And you would probably be correct. It isn't all of that simple. What we need is a better way to do this. And yes, we have better ways. And once again, let's move on to another trick. But series parallel reduction is something that you will use throughout the semester. At this stage, let's turn our attention to divider circuits. We're going to start with the concept of a voltage divider. The idea of a voltage divider is that you have a circuit that has one voltage, and that voltage perhaps easily available to you, and you can access it. However, it's not the voltage you need. You need a different voltage for some purpose. An example that I've seen in real life is that you perhaps engineered a small device that only requires 5 volts. And rather than you creating the 5 volt source, you have been told that this device is going to interface with a more complicated network, and that more complicated network is going to have a place for you to plug in and it will supply you the 5 volts. However, the other more complicated network is actually built by another engineering firm, not your engineering firm. So when you bring your device to actually plug it in, it doesn't have 5 volts. Instead, it has 12 volts. Where it should supply 5 volts, instead it's supplying 12 volts. Okay, well, you can complain to the other engineering firm and perhaps in time they will solve the problem. However, you need an immediate solution. So what you can do is you can divide the 12 volts to be 5 volts that you need through a divider circuit, through a voltage divider. Okay, Now that you have a concept of what the divider circuit may be used for, let's dive into it. Let's start with a really simple circuit that has one source and two resistors. Here it is. We have some supply voltage here, and our resistances are R1 and R2. There's going to be a current set up through this. Let's call that current I. And because everything is in one loop here, everything has exactly the same current. Now the voltages across these two things, because they are in series, are going to add together. Let's call that V1, and we'll call this one V2. Their polarities are like that. Now this circuit has one current, but it really has three voltages now, V1, V2, and V sub S. However, because of the way series circuits behave, you know that V sub S is equal to V1 plus V2. That has to be the case. You also know, based upon Ohm's law and KVL, that the voltage across 1 is really I times R1. The same current is in both of these, so we don't need a subscript on the I. Plus I times R2. Okay, well if that's the case, this is what V sub S is equal to. I can factor out the I and realize then that I, when I solve for it, is V sub S over R1 plus R2. Then, with that recognition, I can write an equation for voltage 1. Voltage 1 is just I times R1, and this is I here, so I can write that as V sub S over R1 plus R2, that's I, times R1. And for voltage 2, I could write that as V2 equals I times R2. So that's V sub S over R1 plus R2 times R2. Okay, I'm going to take these two things and I'm just going to rearrange the terms a little bit. And I'm going to write V1 is equal to V sub S times R1 over R1 plus R2. And V2 is equal to V sub S times R2 over R1 plus R2. These two equations right here are called divider equations. And what these do is they tell you what fraction of V sub S goes to V1, or what fraction of V sub S goes to V2. Because what's here inside the parenthesis is just a fraction. It's R1 over the sum, or R1 over the equivalent resistance, or R2 over the equivalent resistance for this one down here. So it's a fraction. It's because R1 is always going to be less than the combination of R1 plus R2, this is going to be some fraction that's going to be less than 1. You can think of it as a fraction, or you can think of it as a percentage. Whatever it is, it's the portion of V sub S that is V1. And this is the portion of V sub S that is V2. So you can tell that V1 and V2 have to add up to be V sub S, but how does the voltage divide across V1 and V2? Well, it's given by these. These are the divider equations. Now, if we had the situation like what I mentioned, let's say that we have V sub S is equal to 12 volts. But what I want is I want a voltage that's 5 volts. Now, I could attach a wire here and a wire here and measure that voltage there. And let's say that we know that that voltage is V2. That's what I want to be 5 volts. So I want a situation where V2 is 5 volts. Well, if that's the case, then what is V1? V1 has to be 12 minus 5, or 7 volts. It has to be the case. All right, now how do I achieve that in a circuit? Well, this ratio right here, V2 over V sub S, is 5 volts divided by 12 volts, and that is the ratio that I want for these two voltages. Well, what is that? V2 over V sub s, just look at this equation right here, divide by V sub s. That's equal to R2 over R1 plus R2, like that. So if I take this, and now I multiply through, I'm going to have 5R1 plus 5R2 is equal to 12R2. And if I take the 5, put it over here, that's going to be 7R2 is equal to 5R1. And I can see that this ratio of my resistances here, the ratio of R2 over R1, has to be 5 over 7. And it has to be that if I want this ratio of my voltages to be 5 over 12. So if I want to build a circuit like this, a simple voltage divider circuit like that, that has 7 volts for V1 and has 5 volts for V2, then I need the ratio of my, 7 and 5, I said that correctly. But I need the ratio of my R1s and R2s to be this, that R2 needs to be 5 if R1 is 7. Now, that's the ratio. That's not the value. It could be that this is 50 and this is 70, or this is 500 and that's 700, or this is, I don't know, 1.666 and this is 2.333. Okay, as long as the ratio is 5 to 7 for R2 to R1, then you will have this output for your voltage. All right, so let's do a quick little problem here. Let's say that I have a source and these resistors. I have a 10 volt independent source, a 10 ohm resistor is in parallel with that source, and then I've got these two resistors here at the end, and let's say this is voltage 1 and this is V0. What I want to do is I want to find V0, and while I'm there, let's find V1 as well. All right, now, because you know the voltage divider equations and you've committed those to memory, you have committed those to memory, correct? You can, at this stage then, if you have, just write down the equations for what these are. You don't need to solve anything. You don't need to jump through hoops. You don't need to worry about KVL and KCL. You just write down the equations. Here's the way you do it. Voltage 1. Well, I can see that the voltage across this 10 ohm is 10 volts. So this is like that 10 ohm is not even there when it comes to the voltage. Now, it's important for when I'm calculating currents, but if I'm just calculating the voltages here, then this voltage, V1, is just 15/20ths of 10 volts. So V1 is 15 over REQ, which is the sum of these two, 20, multiplied by 10. So 150 divided by 20. Is 7.5 volts. There, I just figured out V1. Do the same thing for V0. V0 is going to be 5/20ths of the supply voltage, which is 10 volts. So that's 50 over 20, which is 2.5 volts. Okay, very quick, let's do a check. 5, 5, 0, 7, carry the 1, 8, 9, 10. 10 volts. That's exactly what we would expect for the supply voltage there. Okay, so it worked out nicely. I would recommend that you seriously commit the divider equations to memory. They are so useful, and dividers pop up repeatedly over and over and over again. Even in a very complicated circuit that doesn't look anything like this, you might recognize in it a divider, in which case you can immediately write down an equation for a divider. And we will encounter those situations, so I recommend you be able to do that. Now, what happens with voltage dividers can also happen with current dividers. If I have a current source that looks like this, I sub s, and a couple of resistors that are in parallel to that. This is resistor 1, this is resistor 2. Now this current coming from the source is going to divide. Some of it's going to go down this way, and some of it's going to go down that way. This let's call I1, and let's call this I2. Now you know that everything here is in parallel with each other, so this voltage, V plus minus, is the same voltage across everything. If I were to take this and build an equivalent circuit out of it, this would still be I sub s, this would still be V plus minus, but this would be Req, the equivalent resistance of R1 and R2 combined, which is R1, R2 over R1 plus R2. Now, the voltage across the parallel resistors are the same. So the voltage, V, is equal to I1 times R1, and it's also equal to I2 times R2. That has to be the same. Okay, but that's also equal to I sub s times Req, times the equivalent resistance. So it's the same over here, I sub s there. Those are all equivalent statements for what the voltage is. Well, I'm going to take Req and I'm going to substitute this in right here. So V equals R1, R2 over R1 plus R2 times I sub s. And that's for the entire thing. However, I could write this. I1 is going to be then solve for this out of I1. Look, this is equal to that. So in other words, let me do it here. Here, I'll do that. I'll start over here and say this way. Based upon this equation here, I1, R1 is equal to this here. R1, R2 over R1 plus R2 times I sub s. So if I get rid of the R1s, then I see that I1 is equal to R2 over R1 plus R2 times I sub s. There. That's a divider equation for a current divider, like you see here. The current that's coming in is divided into I1 and I2, and this is the dividing equation. Similarly, if we did the same sort of thing by setting this and this equal to each other and solving for I2, that's a 2, then we would get R1 over R1 plus R2 times I sub s. So here's another divider equation for this second current. Okay, so these, once again, are very useful equations to have under your belt. Now, I want to show you the parallels then between these. When we were talking about divided voltages, we had two voltages, V1 and V2, and we said those are resistor 1 divided by R1 plus R2 times the source, and V2 was R2 over R1 plus R2 V sub s. Those were the voltage divider equations. When we were talking about the current divider equations, they look like this. And if you look here, once again, think of this that's in the bracket there. That's the percentage or the fraction of V sub s that is going to V1. And the same over here. What's in the bracket is the fraction of the total current, I sub s, that's going to I1 or I2. And you can see that what's in the brackets are almost identical except for what's on the top. If I am trying to find voltage 1, then I use resistor 1. If I'm trying to find voltage 2, then I use resistor 2. However, when it comes to the currents, we have the opposite here. If I'm trying to find current 1, I put resistor 2 on top. And if I try to find current 2, I put resistor 1 on top there. So I just want you to see that pattern that's there, because it may help you memorize then these divider equations and commit them to memory. And you do honestly need to be able to do that. So let's go look at an example now where these divider equations may be helpful to us. Now this is an example that's somewhat similar to one that you've just seen previously. However, in this case, I want to find the current and the power in the 6 ohm resistor here. So I want to find I sub C and the power that the 6 ohm is dissipating. This is very similar to the previous problem that we worked. Now, in the past, what we had to do is we had to calculate I sub A, I sub B, I sub C. We could also talk about I sub D here if we want to, but it's not going to be important because we're only interested in what's happening over here at the 6 ohm. But look, now series parallel reduction can be used, but it doesn't have to be used quite as much. Look at this. If I combine these two together here, that's a 6 and a 4 in parallel. That combination there is also in series with this 1.6. So I can take this circuit and redraw it like this, where this now is the equivalent of these 3 things combined. So let me show you a typical notation that's used. I have a 4 that's in parallel with a 6. So 4 parallel with the 6. That's a common notation, and when you combine those things, you're going to combine them in the correct way for resistors in parallel. It'll be product over sum. But then add to that the 1.6 ohm up there. Now, if you do that, that's going to be 4 times 6 over 10 plus 1.6. 4 times 6 is 24. Divided by 10 is 2.4 plus 1.6. It's going to be 4 ohms. So it's 4 ohms. So this resistor here is a 4 ohm resistor. Now that I have that, I can figure out what these currents are just by looking at it, pretty much my inspection. I should be able to write down an equation for I sub B. And I sub B is equal to what? 16 over 16 plus 4 times 10 amps. So I sub B is 160 over 20, or 16 over 2, that's 8 amps. So I sub B is 8 amps. Now that I realize I sub B is 8 amps here, then that's the current that's coming into this junction right there. And now I recognize that I sub B coming in is now going to be split between these two currents here. So I should be able to write down an equation for I sub C just by inspection. I sub C is going to be 4 over 6 plus 4 times 8 amps. So 32 tenths, or 3.2 amps. That's I sub C. So now that I know what I sub C is, I've got that. That's I sub C. What about the power for the 6 ohm? Well, the power for the 6 ohm is going to be I sub C squared times 6 ohms. So that's 3.2 amps squared times 6 ohms, and that turns out to be 61.44 watts. There. So we used divider equations, specifically current divider equations here, to solve that a lot more quickly than going through the entire process of series parallel reduction. We did combine these three resistors to get the 4, but once I had this, I recognized, oh, now I have a current divider here. I've got 10 amps going into this junction, and I sub A and I sub B, I can write down the equations, and I did that for I sub B right here. Once I knew what I sub B was, I recognized, okay, this is a second current divider. I sub B is coming in, but it's being divided into I sub D and I sub C. So I can write an equation for I sub C. It's going to be 4, that resistance there, divided by 6 plus 4 there. And 8 amps is the current that's going into that junction, and it just falls out after that. After I've figured out what I sub C is, then the power for the 6 ohm just falls into place. Okay, that's all good and well. Okay, there's one thing that I specifically want to talk about regarding voltage dividers, but I'm going to save that for the next video. Let's stop here and we'll pick up with our discussion of voltage dividers next time.